Very good. Okay. Welcome to Thursday, November 12th. And we're working in our last two sections of chapter 7 today. And chapter 7's been about radicals and things we can do with radicals. That's how we're going to end. Each section has been kind of compartmentalized, like, okay, in this section we're doing this, in this section we're doing that. And that's going to continue today. So a lot of problems that look all alike, and you just have to learn a couple techniques that you have to be careful about, and then you'll have the use of these problems. It depends on what your experience has been in the past. Maybe some people have heard about complex numbers before, maybe some people have never heard about them. Don't worry about it either way. All the normal backups, even down to your calculator, which does execute complex numbers completely effectively. But we're going to do the first hour equations with radicals, and then the second hour complex numbers and complex arithmetic. And this is preparing us for an important mission in chapter 8. Okay, I have another homework posted for you later last night because I've been a little bit behind on things. So you have another homework you're working on written, and you have the XYZ homework as normal. So let's talk about equations with radicals just quickly, and then you'll understand what you're supposed to do and what the unique twist is in equations with radicals. So if I write this on my paper, be really careful if someone gives you this thing right here to solve. And what I want you to be careful of is you don't just rush and spit out an answer like, oh, square root 16, 4. Because I'm not asking you for the square root of 16, but I'm asking you for a number that I would take the square root of to get 16. So this number x must be a bigger number. It's logically a bigger number than 4. In fact, even if you wrote on your paper x equals 4, the moment you tested it, then you would say, no, it's not 4. Square root of 4 is 2. But how do you get to x right here? You get to x the same way you get to x in anything. So there's one new twist. For example, if I said to you x minus 1 is 16, then you would say, okay, x subtract 1. I'll get rid of that minus 1 by adding 1. X is 17. If I said 2 times x is 16, you'd say, okay, I'll get rid of that 2 by dividing. X is 8. If I said x over 4 is 16, you'd say, okay, I'll get rid of that dividing by 4 by multiplying by 4. X is 64. So what you do in each one of these cases is what you do all the time. You're trying to isolate the x. You're trying to unwrap it like it was a present in a box. And that means you're supposed to undo whatever is being done to it. Let's add 1. Let's divide by 2. Let's multiply by 4. So here, what's being done to the x is the square root. And then you say, well, what should I do to undo the square root? To unsquare root something is to square it. And so I'm not saying that this is super creative or anything. I'm just saying I want to get rid of a square root. I will square both sides. I'll square both sides to make it fair. If I just squared one side, I wouldn't be keeping the equality. And then x is 16 squared, either from your multiplication tables or from your calculator. That's 256. Notice that because this is a square root, I didn't say anything like plus or minus 256. I wasn't taking a square root. I was undoing the square root. 256 square root is 16. But square root of minus 256, that's not allowed yet, although it will be in the second hour. So you deal with an equation with a square root in it just by squaring both sides. If it was a cube root, you would deal with the equation, the cube root of cubing both sides. We'll do an example there too. But there's something you should be careful about. And that is why in these problems, you're going to always required to check your answer. So make sure that you don't just take this answer and accept it as being the actually working. I'm going to take this 256, set it in there. Square root of 256 is 16. I know the square root of 256 is 16, but I don't mind typing that in front of you. So with radical equations, these are called radical equations, you always have to check your answer for even roots for this reason. When you have a sentence that's true, and you do the same thing to both sides, like add 10, divide by 4, subtract 3. As long as you do the same things to both sides, the sentence remains true. Even if that same thing is squaring. So when you square two sides of an equation, you don't create falsehood. If these things are equal before and you square them, they're equal after. But the problem with squaring something or any even power is you might take things that are false and make them true. You know, for example, minus 2 equals 2. Well, of course, that's ridiculous. No one would write that. But look what happens if I square both sides. You can predict what's going to happen. 4 equals 4. What did I just get? I just got a true sentence by doing something fair to both sides. I just got a true sentence by doing the same thing to both sides. Usually we're not trained to look like that. Usually you're trained to say, if you do the same thing to both sides, you're okay. So you are, but in this case, squaring, anytime you raise two sides of an equation to an even power, not an odd power, but an even power, you can actually take things that are false and make them look true. And what that does in an equation like this is sometimes it can make a new equation that has an answer that doesn't work in the original equation. Okay, so let's take a simple example, and then I'll show you an example where you actually get this strange failure. So I'm going to look at problem 1 just to go through this straight ahead. Two x plus 1 equals 3. Now, I'm going to approach it like I did the problem with the 16 above. I'll square both sides of this equation. Because the way to get rid of a radical, get rid of a square root, is to square. The way to get rid of a cube root is to cube. And when I do that, I get 2x plus 1 on the left, 9 on the right, and now I've got an ordinary problem. I'll finish it by subtracting 1 and dividing by 2. And you don't even sense any danger here, but let's test it to make sure. Stick the 4 in here. I don't mean that you have to write everything down necessarily, but just take this up here, put it in your calculator, check it, whatever, see if it works. When I put the 4 in here, I get 8 plus 1 is 9. Square root of 9 is 3. I'm okay. Let's look at problem number 7. 5x minus 7 square root equals -1. And now if I want to get rid of the square root and I square both sides, watch what happens. -1 times -1 is 1. Square root of 5x minus 7 squared is 5x minus 7. Again, it looks very innocent. And I'll just add 7 to both sides. 5x equal to 8. Excuse me. X is equal to 8 over 5. But when I place this in the original problem, I always go back to the original. 5 times 8 over 5 is 8. 8 minus 7 is 1, and the square root of 1 is 1, not minus 1. What are you to do? You did everything by the book. You only came up with one answer, but it doesn't work. Well, then all you can say is this problem has no solution. That's your answer. Sometimes the answer is that there is no answer. Now you say, oh, well, you made it that way because you set the square root equal to -1. And everybody knows the square root can't spit out negative numbers. So this was never going to work. And I agree with you. It was never going to work. I just want to show you that if you just went straight ahead, followed the rules, you get an answer, but the answer doesn't work. You can always follow the rules, check your answer. But I want to show you, as we go through some more problems, that sometimes it's not so obvious that it's not going to work. We'll just be doing something that looks pretty ordinary, and then the answer doesn't work. So the reason why I get caught in this trap is when I use that squaring of both sides, fourth power of both sides. If I cube both sides, there's no problem. For example, let's try. By far, we're doing problems with square roots more often. But let's do problem 18, which has a cube root, just so you know that you can do this with any root. So we gotten what right here on number 18? Cube root of 2a plus 7 equals -2. Okay, I want to get this a. I want to find out what a is. Several things are being done to the a. Somebody doubled the a, then somebody added 7, then somebody took a cube root. So I got to unwrap this like a Christmas present. And the first step in the unwrapping is to get rid of the cube root. How do you unwrap a Christmas present? From the outside in, right? First you take off the bow, then you unwrap the paper, then you open the box, then you see the present. Okay, let's cube both sides to take off this cube root. And maybe in the back of your mind, you're saying, oh, no, negative number, it's not going to work. But remember, cube roots can spit out negative numbers. Cube roots can swallow negative numbers and spit out negative numbers without a care. This is 2a plus 7. Negative 2 cubed, make sure you multiply that right. Negative 2 times negative 2 times negative 2 is negative 8. Then you can subtract 7 from both sides. Then you can divide by 2. Negative 15.5, negative 7.5. I'm used to saying negative 15.5, but I wouldn't be upset if you wrote negative 7.5. It'd just be not common. More people would like you to write it with a fraction. Improper fraction, this is called, when the numerator is bigger than the denominator. So let's take the negative 15/2 and put it back in here just to check. 2 times negative 15/2 will be negative 15. Negative 15 plus 7 will be negative 8. And the cube root of negative 8 is negative 2. So this answer is correct. And I'll just tell you, if you do all the steps right, you don't have to worry about the odd roots. You're not going to cause any damage when you raise two sides of an equation to an odd power. Only when you do an even power. Okay, let's try again. So let's just pump this up slowly. And try problem 22. Because it's not as short as I've been portraying in the first few problems. Let's say I got a plus 10 square root equals a minus 2. Yeah, now I'm going to square both sides. But now I got to remember my rules of exponents. I got to honestly square both sides. And squaring the square root is not difficult. That just gives me a plus 10. But when I have these two things, a minus 2 squared, I got to remember that a minus 2 squared is something I have to FOIL. So you have to be prepared to FOIL this out. When you FOIL that out, it's not impossible. Just say a squared minus 2a minus 2a is minus 4a. Minus 2 times minus 2 is plus 4. And that's what you write here. See, a lot of people just rip right through this and say, oh, a squared minus 4. No, that's not how you FOIL something. So I'll write a squared minus 4a plus 4. And this is the style of problem we've done once where I gotta hope I can factor this. Let's bring the a and the 10 to the right side. Subtract a squared minus 5a, subtract 10. 4 minus 10 is negative 6. And this can be solved if I can factor it. And this one factors, thankfully. A. Sometimes you jump on 3 and 2, but it's not going to work here. Two numbers that multiply to 6 and differ by 5. That would be 6 and 1. And I want more negatives, so I'll do negative 6 plus 1. So a plus 1 is 0, or a minus 6 is 0. A is minus 1, or a is 6. But now you're so proud that you did that work that you might just circle these and go on, and you'd be wrong. You got to check. Anytime you square both sides of an equation, you got to check. And in fact, one of these doesn't work. I'll try the one that works first, the 6. 6 minus 2 is 4. And 6 plus 10 is 16. The square root of 16 is 4. I didn't write out what I just said. I just said, okay, I'll put it in. I see square root of 16 on the left. I see 4 on the right. But with this -1, you're in trouble. Because on the left, you'll get the square root of 9, which is easy enough. But on the right, you'll get -3. And that is not true. The square root is the positive square root, the principal square root. So this is not true. And that means this answer is not going to work. So there's only one answer to this problem, a equals 6.
Hey, Professor, I have a question.
Go ahead.
So if we couldn't factor it, what would the answer have been?
Very good. And here's his mission. He thinks factoring is so important that everything he's given you so far is factoring. And then you've got to ask the very natural question, what do I do if I can't factor? And that is what we'll cover here in the next chapter. And you may have heard of that, the quadratic formula. So when you see one of these right now, I don't think we've ever seen one that didn't factor. But that doesn't mean, say, what happens when it doesn't factor? I'm stuck. No, there's just a really famous formula called the quadratic formula. And even if we haven't used it yet in here, you may have heard of it. If you haven't heard of it, don't worry. But this formula will solve that problem if it cannot factor. And most people, like somewhere they've heard of it or used it. Maybe they're not so familiar with it. Maybe they're a little bit rusty on it. But this is called the quadratic formula. And so we will do problems exactly like that in chapter 8, where you cannot factor and we got to pull out this formula. Be careful when you use your vocabulary here. That formula is called the quadratic formula. This kind of equation is called the quadratic equation. Sorry, equation. So don't call this the quadratic equation. This is a quadratic formula. Don't call one of these a quadratic formula. It's a quadratic equation. Okay, so this is the major problem today, is you do everything right, but you forget to check. You have to check every one of these square roots problems. And sometimes the problem is going to get busier than this. I'll show you some busier one now. But always, always, always check whatever answers you produce in these problems. Let me try another one. So I'm just trying to pick which one I'm going to pick. What happens if he throws 2 square roots in the problem? And the answer is that could make it not too bad, or it could make a lot of extra work. So first, let's try 2 square roots that doesn't turn out too bad. Number 34, for example. It's kind of funny, and I've been a little bit sloppy here so far in the paper. I've been writing down these problems and never telling you the instructions. The instructions each time are solve, 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 solve. Find the numbers that work. But just these problems are so focused on solving, I didn't even think about that I should write down solve. This is an equation. I'm finding the number that makes the sentence true. I'm solving. Okay, so 2 square roots, but they don't appear too threatening in this sense that you realize that once I square both sides, I won't have to look at either one anymore. So that's what I'll do. I'll have 2y plus 5 on this side. Here I'll have 5y plus 2 on this side. I usually don't make much fuss about what side I put the variables on. I usually like the variables to be on the left. Subtract 5y. I also don't like to have negative numbers on my variables if I can avoid it, but it's not a bad thing. I'll just divide by -3. So long as I keep my sign correct, I'm okay. Divide by -3, divide by -3, y is 1. Now the check. And notice sometimes you get 2 answers, sometimes you get 1. Here I only got 1 answer. Now the check. If I stick a 1 in here, 2 plus 5 is 7. Stick a 1 in here, 5 plus 2 is 7. Now, I don't know what the square root of 7 is, but the left side and the right side are exactly the same. So this works. When I say I don't know what the square root of 7 is, I don't know the decimal that goes on forever that's equal to the square root of 7. That's something I'd use a calculator for. So I do know that these are the same. So I do know that this answer worked. I just don't know the square root of 7 off the top of my head. It must be 2.4-ish. But now I'm curious. Oh, I was a little bit underestimated to 2.6457. Kind of begs the question, like, how did people do square roots before calculators? You can work out square root with a paper and pencil if you know a little algorithm. Maybe someday I'll show it to you, but nowadays everybody just uses calculator anyway. But there's a way I could write down the digits of a square root one step at a time. It just take a few minutes, but it's not impossible. Okay, good deal. Here's the first problem we did with 2 square roots, and it wasn't too bad. But let me show you that sometimes this could get messier. 2 square roots is a signal that the problem might require extra work. Okay. Let me just get my pages numbered here so I keep track of stuff. So look at 37. If I had the square root of x minus 8 equals the square root of x minus 2. So this is a very common problem that people get caught on because they don't square it legally. You think about, okay, it doesn't look very much different than the last problem. There were 2 square roots in the last problem. There's 2 square roots in this problem. It even looks smaller than the last problem. What's your issue? But the thing that makes this extra work is this part of the right side has a square root and part of it doesn't. But let's just go straight ahead. Let's just go like we tried every other problem. Let's square both sides. Because so far that's worked. And it will work here if you square properly. So now I'll square both sides. And where I have this square root isolated by itself, that's just x minus 8. But here, I'm going to have to FOIL. Like I FOILed right here on this problem. To take a minus 2 squared required me to FOIL because I had 2 pieces separated by that minus sign being squared. So whenever you square things, two pieces right here is a binomial. This is one piece, one square root. This is a square root and something else, two pieces. So I have to FOIL this. And sometimes people just say, oh, it's x minus 4. But then you're just wrong. You have to remember that this has to be FOILed out. You can write it on the side and do it on the side if you want to. There's nothing wrong with that. But you've got to FOIL this out. Root x times root x is just x. Root x squared, x. Then I'll have a minus 2 root x and a minus 2 root x. That'll be minus 4 root x. And then minus 2 times minus 2 will be plus 4. So I don't just have x minus 4. I don't even have x minus 4. I have x plus 4, but I have this middle term where, unfortunately, I still have a square root. This problem is still a pretty mild problem, but you see I'm not even, well, kind of like I'm half done because I got to do it again. Now let's see what I can do. I mean, I've got a square root in the problem. I'll square both sides. That'll get rid of the square root, sure, but I don't want to carry all this stuff with me that I don't need. So let's organize it first. I can subtract x from both sides. So actually there's no need to keep that x. I could subtract 4 from both sides. In fact, even though I've gotten this down pretty small, before I do any squaring of people, why don't I just divide both sides by minus 4 and make it even shorter? So here I am. And it's not going to be hard to finish this, but you notice that I'll have to square both sides again. Maybe you already see the answer right here, but just to make sure everybody sees the answer, I'll square both sides. X equals 9. And then having done all that work, don't forget that you're going to check it. So I'll just write this on the side. 9 minus 8. Is that the same as 9 minus 8 square root? Is that the same as 9 square root minus 2? 9 minus 8 is 1. Square root of 1 is 1. Square root of 9 is 3. 3 minus 2 is 1. Yes. So everything worked out, but I actually had to square both sides twice to really kill the square root. You know, like first time I squared both sides, I killed one square root. But it took me a second time to kill the second square root. That's what can happen to you when the problem has two square roots. Okay. This was still wasn't too messy. And it's not even a super long problem. It's just that it's very common for people to mess up right there if they don't remember to FOIL. You usually get into trouble. I'll write this down. You usually get into trouble if you don't FOIL properly, or if you don't FOIL at the right place. Right there. Okay. But here's the good news about today. The problems in the section, all the problems in the section are just like I showed you. That is like the worst case scenario there maybe. Here, let me see if I can pick an uglier one. You know, if you had two square roots on one side, then you just move one of them to the other side, like 41, 43, 44. I'm just looking at other problems. Let's try 42. 43, 44. Sometimes, now, you know, still this warning, always check. Maybe I should write that down. You usually get in trouble if you don't FOIL at the right place, or if you forget to check your answers. These problems, you always check your answers. But sometimes the problem is you can't predict when the answers are going to go bad. So that's why it's almost seems random. It's not random, but it almost seems like you can't tell which answers are going to go bad, which answers are not. So let's look at 42. Yeah, that's a reasonable one. And then, although it's a little bit uneven today, I might take a break right there because the stuff we're going to do in the second half will require a little more time. This section 7.6 that we're finishing here. This is not as complicated as what we have to do next. Okay, here's problem. Square root of x plus 5 equals the square root of x minus 3 plus 2. And here I've got two things on this right side, so when I square, I'm going to have to FOIL. That's my issue. So we just have to get into it. Let's square this side. I don't know if it helps to introduce a different color just to get your attention. But the foiling here is kind of messy. Some people just forget to do this because it's like seems like too much work. So here, let me write it out where I FOIL this out carefully for you. It can be a lot of writing, I understand, but it's just ordinary FOILing. Root x minus 3 times root x minus 3. And that's just the square root of x minus 3 squared. Anytime you multiply a root by itself, you just get what's on the inside there. So that's x minus 3. Then I have plus 2 times the square root of x minus 3 and plus 2 more times the square root of x minus 3. So that's 4 times the square root of x minus 3. There's nothing I can do to make that simpler. And then the last piece of the foiling is the plus 2 times the plus 2. I can combine this, sure, but I had to FOIL it properly. When I combine it, I get x minus 3 plus 4 is plus 1, plus 4 times x minus 3. So it doesn't hurt to do this out on the side if you know you're going to have to FOIL anyway. You could do this out here on the side and then bring it into the problem. Okay, let's bring it over to the problem. So when I square the left side, I get x plus 5, and that's not more complicated than that. When I square the right side, I get this x plus 1 plus 4 times square root of x minus 3. Again, I get to cancel some things, sometimes just combine, but here I get to cancel even, cancel the x. X minus x, there are no more x's. Those are gone. 5 minus 1 is 4. And I have 4 times square root of x minus 3 on the right. So I combine the 5 and the 1 to make 4. Now I'll divide by 4, just so it gets easier to look at. Okay. Now I'm on a roll. Still got a square root, but one more squaring and I'll be done. So 1 is equal to x minus 3. If I add 3 to both sides, x is 4. Sorry, move my paper up. But do not circle this until you check it. Let's get back up here. You can just scribble the 4 in here. Okay, 4 plus 5 is 9. Square root of 9 is 3. 4 minus 3 is 1. Square root of 1 is 1. So is square root of 9, 3, equal to square root of 1, 1 plus 2? And the answer is yes. So you're okay. So you can go circle that number. So really, these are not terrible problems. It's just people don't, maybe they like don't like to FOIL ugly things. So they just decide to skip it, but you can't do that. As long as you're paying attention to the FOIL when you have to and check your answers, you can always get these right. It's not so bad. Okay, what I want to do here, even though this is usually like 10 minutes ahead of schedule, I'm going to let you take a break. I'm going to stretch my legs early because the next thing we're going to do is a little bit longer than this. Not harder, just a little bit longer. So this way we'll do it all at once and not interrupt it. So I'm looking at 1246, 1247. Let's say, let's get back together at 12:52. Kind of an early break, breaking before the top of the hour. Okay, I'm going to mute my microphone, just stretch my legs for a second. You're welcome to do the same. Okay, sorry. Extra minute outside. Problem is some of this warm weather. And you can be thankful for the warm weather. But then the woodpeckers are coming out and poking holes in the side of your house. Especially if the sun's warmed up beside your house, the woodpecker thinks that's just fun to sit there and bask in the sun and poke holes in your house. So I had to shoo away the woodpecker. Unfortunately, that's pretty temporary. So that probably means in the spring I got to patch up a lot of silly tiny holes in the house. Okay. So this is a topic that is just kind of famous for people not knowing what to do with it. It just, even if it doesn't bother you, people just say, like, so what? What do I do with this? What am I going to do with this? And it could be that some of you have never seen it before. In which case, I still got to treat everybody at the same levels, not to bore some people or not. But I have to tell you about this and tell it to people as if they were doing it the first time. So what I'm going to do, the reason why people don't see a great need for this is they don't always understand the purpose of the complex numbers. Maybe if I give you a reason, a little bit of reason why there's a need for this, then it won't seem like so abstract or so like not real. So for a few minutes, think about kind of the progression or the evolution of solving equations. And the idea that to solve an equation means you got to have the number at hand that does the job. Sometimes you have to make up new numbers. So if I say to you, 2x minus 4 equals 0, you're going to solve that without doing any steps. You just say, oh, I know the answer. The answer is 2. Even if someone challenged you, you wouldn't be fazed in any way because you could just take the 2, stick it in there. 2 times 2 is 4. 4 minus 4 is 0. So you got the problem, you got the answer, you can back it up. You're very, very happy. But now look at this equation. 2x minus 7 equals 0. And you're likely to be just as fast with the answer. X equals 7 over 2. Or 3.5. But then you run past this idea of the fractions. What do you mean 7/2? What does 7/2 mean? There was a day where you did not know what 7/2 meant. When do people mostly learn fractions? Third grade, fourth grade, sometimes all along the way. But this idea that these two equations are different, and this equation looks so easy because 2 is such a simple answer to see, but this equation, which looks very much the same, has a different looking answer. And if you didn't understand what the fractions were, you'd be searching for the answer to that problem. Is it 0? No. Is it 1? Is it 2? Is it 3? Is it -1? Is it -2? You could search all these whole numbers and none of them would work. And then you'd say, I guess there's no answer. Until the day someone invented this 3.5. And not only had to convince you that there was such a thing as a ratio, they had to convince you how to add, subtract, multiply, and divide them. They came to you, and maybe it's not hard for you to think backwards. Maybe you can think backwards better than I can, because for me, this would be very, very long time ago. Teacher came to us and said, okay, we've got these new numbers today. They're called fractions. And your first reaction is to rebel. What does 13/7 mean? But your teacher patiently said, okay, fractions is something like numbers. You can add, subtract, multiply, and divide them. Here's how you do it. And after teaching you for a while, add, subtract, multiply, divide, then you accepted the fact that they were numbers. And it's kind of like if it walks like a duck and if it quacks like a duck, it's a duck. So at first, you didn't think of this as a number, but after you learned how to add, subtract, multiply, and divide them, you did. Okay, let's try it again. X squared minus 4 equals 0. Well, this time, because you've been practicing, you can factor that. You can say, oh, I know what makes this sentence true. -2 or 2. If I square 2, then I will get 4. And then the sentence will be true. If I square -2, I'll get 4. The sentence will be true. So again, at first, these answers seem so quick to you. But what about the day where someone told you to do that? X squared is equal to 7. And you ran through your numbers. 0 squared is not 7. 1 squared is not 7. 2 squared is not 7. 3 squared is not 7. 4 squared is not 7. And what did you say to someone? There is no number whose square is 7. Until someone invented one. And just say, well, yes, there is. It's square root of 7. It's somewhere, must be less than 3, because 3 squared is 9. Must be more than 2, because 2 squared is 4. 7 is between 4 and 9. So the square root of 7 must be between 2 and 4. Sorry, 2 and 3. And then they tried to shortcut this situation by handing you a calculator and saying, look, square root of 7, 2.64575. Now, if you multiply this number out by itself, you'd get darn close to 7. Oh, not 2 3s, 1 3. In fact, even misleadingly close to 7. Notice the calculator just says, oh yeah, square it, get 7. But this number goes on forever. When I square it and the calculator responds 7, what the calculator is saying is, that is so close to 7, I can't tell the difference, which is okay. But you just realized that there was a new in-between number. Like 7/2 was in between 3 and 4. Now there's a new number in between 2 and 3 called the square root of 7. And recently, we were just working with square roots, simplifying them, adding them, subtracting them, dividing them. But you've done work with square roots before in some ways. Okay, now I got to open your mind just one more step.
Hey, Professor, can I ask a question?
Go ahead.
When you did the x squared minus 7 equals 0, or not, the x squared minus 4 equals 0, couldn't it also just be the absolute value of 2?
Oh, that's another way to say it, and that's a fine way to say it. You could
I was just wondering. I just wanted to make sure I kind of had that rule down.
say it this way, though. I'd change the order of your words. Say, don't say x is the absolute value of 2. Say the absolute value of x is 2. So, and people get this by doing that. So I don't mind if you say this. X squared is 4. Then people take the square root of x squared, the square root of 4, and the square root of x squared, if x could be plus or minus, is legally the absolute value of x. So that's why people say it that way too. It is the same answer either way.
Okay, thank you.
But now let me give you this equation. X squared plus 4 equals 0. Or x squared is minus 4. Now you really rebel. And you say, no, no, no. I've learned from 6th grade on that when you square a number, you'll never get a negative number. And the answer is right. You take every one of these numbers on the number line. It doesn't matter what you square, you never produce a negative 4. When you square 1, 2, 3, that produces positive number. When you square 3.5, it produces positive number. When you square 7 root, it produces a positive number. When you square negative numbers, you get positive number only. So then we're trained, and even we facilitated this most recently in the past couple of weeks by saying, don't take the square root of a negative number. You're trained to say, there are no numbers whose square is negative. But the right thing to say is, there are no real numbers whose square is negative. Just like we had to invent fractions and we had to invent square roots, it could be that I just need to invent another number system. You had to invent fractions. It wasn't going to be one of these happy tick marks on this line. And then the square root of 7 wasn't even going to be one of the fractions on this line. Well, if I find a number whose square is minus 4, it's not going to be on this line at all. Because any one of the positive numbers I square, I get positive result. Any one of the negative numbers I square, I get positive result. If I square 0, I get 0, not negative. So this thing right here, called the real number line, the answer is certainly not here. But that doesn't mean I cannot make up an answer. So let's invent a number that solves that problem. Let's say, bring the paper down. Let's invent another number. And you say, you can't just invent numbers. And I'm saying it's been happening to you for your whole life. Inventing fractions, inventing square roots. Whenever you want to solve a new problem, sometimes you have to invent a new number to solve it. You know, when someone comes up with some really brilliant idea, it's because what? They came up with the answer that no one else thought of, you know, the answer that was impossible, the answer that didn't exist. And everybody else, you know, kind of rails against it. That's impossible. That doesn't exist until it works. And then people start saying, oh, that makes sense. You know, they suddenly accept it. So let's let the symbol lowercase I stand for this thing that we were forbidden from doing, the square root of -1. Let's just let I equal the square root of -1. Traditional letter. It's called the imaginary unit. And sometimes people in math get a sense of humor and they say, this is not a real number. Let's call it an imaginary number. That doesn't mean it's not a real thing. It just means it's not on the real number line that we're used to counting numbers on. What happens if I is equal to the square root of -1? Well, then the first thing that happens when I square I, I'll be squaring the square root of -1. Let's say that that erases the square root like I normally am used to. So I squared is -1. Now that lets me solve this problem. I did not. Sorry, I was trying to help somebody else there. Now I can solve this problem. X squared equals -4. By taking the square root of both sides. And before I was forbidden from taking the square root of -1. Now, square root of a negative number. Now let's use this letter I to take the square root of -4. Let's say square root of x squared equals square root of -4. X equals plus or minus. You could say with absolute value too in that sense, but I'd rather use a plus or minus here. This is not totally foreign to you. You know what the square root of 4 is. You were just forbidden previously from doing the square root of -1. So let's do the square root of 4 is 2. And let's do the square root of -1 is this thing called I. Now, I proudly announce to people, I've got 2 answers. And they say to you, what's this I thing? You say, don't worry about it. I is just the square root of -1. Or I squared is -1. And of course, they look at you crazy at first, but You looked at your teacher sideways when she told you what a fraction was or what a square root was. So let's just try it. I mean, what does solution mean? Excuse me. Solution means it works. Let's try it and see if it works. 2i squared, is it really minus 4? Well, I'll square the 2 and square the I. When I'm multiplying, I'm allowed to square both pieces like this. Squaring the 2 gives me 4. Squaring the I gives me minus 1, because that's what we invented. Well, we didn't invent it. It was invented a couple hundred years ago. And that's minus 4. So 2i is an answer to this problem. And minus 2i would likewise be an answer, because squaring minus 2 would give you 4. Squaring I would give you minus 1. So what this number does, this number called the imaginary unit, is it opens the door for you to solve more problems. And on the face of it, you may say, I didn't need to solve any of those problems. I don't need to solve more problems. But it turns out that there's lots of problems like this in science and engineering that use this imaginary unit. In electrical circuits, in the equations that civil engineers use to design bridges, or the airplane, the wings on an airplane, how they, take the stress, vibrate, carve through the air. So even though it's not the first thing you learned, it is a new and legitimate way to solve equations.
But how do you apply something that is imaginary to real life applications?
Good. In that sense, I am not equipped to tell you everything you need to know. Now, at that place where you were studying electricity or engineering, then you'd be in another math class. And in that math class, then I'd show you how this number shows up in the electrical circuits. And I do teach that math class. I do teach it next semester. There's a couple more math classes between here and there. That's the problem. But if you, I don't know, maybe you got a mom, dad, aunt, uncle that's an electrical engineer, you got something called an RCL circuit, resistor, capacitor, inductor. So basic electric circuit. It just so happens the equations of the electricity flowing in there depend on using both the real and the imaginary numbers. You have to use both, or you get nothing. You get no solutions. You get no answers. And it has something to do with the way the current flows through those elements. Now, that's the problem, is that's not a very satisfying answer, because you want to know how and why. And I can just say, well, if you're interested in engineering, you're going to come across it, but you're not going to come across it for a couple math classes from now. Right now, all I can do for you is say, are you willing to learn these new numbers? And you guys are. I'm just saying it's harder for me to give you a good example of what to do with them, although the author does a pretty good job of it. You were willing to learn how to add, subtract, multiply, and divide fractions, even though it seemed kind of silly at the time. I mean, think about it. When someone wrote down 7/2 plus 2/3 is 25/6, your first reaction was, you just made that up. You're joking. But then someone showed you how they made the 25/6. 7/2 times 2/3 is 7/3. That doesn't look so weird as long as you learn how to cancel. But you were willing to learn how to do that because somehow you believed that fractions were essential just to doing ordinary things. Maybe they're essential to you every day, maybe they're not. And that's the same thing with these. I would say suspend your disbelief, like, I can't touch it or taste it or smell it right now, so it's not real. Well, you don't ever say that, really. There's a lot of things that are real that you can't touch, taste, or smell. And right now, we're introducing you to a new number, and it's not on this real number line. Let me show you where people put it. So let's say this is the ordinary real number line, because you have done this before. And I'm going to mark it off like 0, 1, 2, 3, 4, minus 1, minus 2, minus 3, minus 4. And let me draw another axis, like you draw the x-axis and y-axis, except let's not call this the x-axis. Let's call it the real number line. And let's call this axis the imaginary numbers. 1 eye, 2 eyes, 3 eyes, minus 1 eye, minus 2 eyes. It's a little too crowded here. I should have made this picture bigger. Sorry. So this is the real number line. Let's call this the imaginary number line. And together, what happens if I took 3 steps to the right and 2 steps up? Well, I'd be at this point. Usually you say 3 comma 2, but I'm going to say 3 plus 2i. This is called a complex number. A complex number is a number that has a real part and an imaginary part. The real part is the 3, the imaginary part is the 2. And this is going to be my new number system. These are called, this whole table of numbers, this whole planet, this whole plane of numbers, called the complex numbers. And instead of saying, which I know none of you are doing right now, but I'm saying, instead of saying, no, those aren't numbers, I've never seen numbers like that before, let's do an experiment. If I could teach you how to add, subtract, and multiply and divide them, just like someone taught you to do with fractions one day, then how can you not call them numbers? What are numbers? Numbers are things that can be added, subtracted, multiplied, and divided. If I show you how to add, subtract, multiply, and divide these complex numbers, it's going to be pointless for you to stop calling them not numbers. It's going to be pointless for you to say, well, they're not numbers because, and I say, because why? You can add them. And then you say, yeah, I can add them. I can subtract them. I say, I'll show you how to multiply and divide them, and then you admit you can multiply and divide them. You know what I'm trying to say to you, and now we got to be ready to do it, is if you can add, subtract, multiply, and divide something, it really must be a number. Just like I said earlier, if it walks like a duck and quacks like a duck, it must be a duck. Now that's common sense English, that's not math. So now let's do the math part. Is it really easy to add two numbers that look like this? And the answer is, even if I had never trained you, I bet you would add these two numbers correctly. Because you got this law burned into your head, says combine like terms. You see the 3 and the -4, and you automatically say -1. You say the 2i and the 7i, and you don't even care what I is. If I got 2 i's and 7 i's, then I got 9 i's. And if I would have told you to subtract them, you would have done it just as quickly. Someone's vacuuming the house upstairs. So clean the inside, clean the outside. So if you're hearing a little rumbling in the background, that's what it is. Okay, let's subtract these two people. How about the part without the I and the part without the I? That's what I should subtract. 3 minus -4. 3 minus -4 is 7. 2i minus 7i is -5i. So what I've just showed you is that if I pick out, now where's -4 plus 7i? That must be pretty high up here. That's right there. There's -4 plus 7i. Right there. And here's 3 plus 2i right here. When I added them, I got -1 plus 9i, which is up here. When I subtracted them, I got 7 minus 5i, which is down here. I'm getting a little bit too littered in this drawing. Now, you may not know what to do with those two numbers that you just added and subtracted, but what you did was logical. And if I gave you any other two numbers, you could repeat it. So now you have to say to yourself, okay, I can add and subtract these. Well, that's halfway to being numbers. Now, before I go into the multiply and divide, there's some people that also say it like this. No, these are not numbers because they're not in my calculator, because I know that when I take the square root of a negative number, my calculator says you can't do that. So let me tell you about what your calculator says. It's true that ordinarily, if you type in the square root of -4 in your calculator, the calculator says you can't do that. But if you look closely at what it says, it's got this funny message right here. There's an error. It's not real. It has a non-real. This has got a non-real answer. So in fact, your calculator doesn't say you can't do it. The calculator just says it's not real. Now, before today, if you had not done this before, then you took that to mean you can't do it. It says you're in real mode and all your calculations must result in a real number. And you say, really? There's another mode? Go down here into the mode. So quit this. Mode. You know, all kinds of things. Radians, degrees, if you're in a trig class. Look at this one down on this line. Real. You're in real mode. Your calculator's in real mode. But look at the next thing next to it, A plus BI. Your calculator does recognize complex numbers. If you go and adjust your calculator, say put it in complex mode, like that, and then ask it what the square root of -4 is, surprise, calculator says 2i. So first it's an error, now it's 2i. And if you ask your calculator, what does it mean to square 2i? And then you see that there's an I key on your calculator down here. So you won't find any calculator nowadays that doesn't have imaginary number built in. So if I square that 2i, what do I get? Oh, calculator says you get -4 because I squared is -1. Okay, so now if you want to be a doubter, then it's going to cost you a little more because it is apparently built into every calculator. Okay, let's try this. If it's built into every calculator, could I just type these things in and get the same answer that I did? Not that I needed because they weren't that complicated. Well, let's try it. 3 plus 2i plus -4 plus 7i. Notice the calculator says -1 plus 9i, just like we did. Because it wasn't hard to do that. Just combine like terms. What if I had subtracted them instead? Here, put a subtraction key in there. Put a subtraction sign. Calculator's not going to blink. It's just going to say 7 minus 5i. Now, I didn't need the calculator to do adding or subtracting there. Sorry, I'm just trying to clean off some screen dirt. I didn't need the calculator to add or subtract those. But it's kind of interesting that it's built into your calculator already. Look under the mode key. Whatever type of calculator you have, it's certainly got TI 83, 84, even the old one's got a mode key. And there's something in the screen that looks like A plus BI there. Let me pull up the older looking one in case you want to see that. Shows up a little bit better on the screen anyway. Under mode, it's got right there. Complex numbers, A plus BI. So if you want to do calculations with complex numbers, just set your calculator into that mode. Okay, now what do we got to do? I think I got to show you how to multiply and divide them. But now you're already a little bit helpful because if the calculator can add and subtract them, the calculator can multiply and divide them. So let's figure out what that works. Well, again, if I handed this to you and you had never seen it before, in self-defense, you would say to yourself, what? Oh, let me FOIL. I wonder if you can do that. Let's multiply these two complex numbers by FOILing. First times first, -12. Outside, 3 times 7i, both positive 21i, inside negative 4 times 2i is negative 8i. Now, last times last, be careful. 2i times 7i, they're both positive. Okay, so positive 2i times 7i. Now you got to do some extra work. 2 times 7 is 14. But what's I times I? I squared is minus 1. So 2i times 7i turns out to be minus 14. Just for fun, if you want to check it on your calculator, 2i times 7i is minus 14. Now let's combine all the like terms, right? So I've got minus 12, 21 i's minus 8 i's is what? 13 i's. So minus 12 plus 13i minus 14. I don't need to write this many steps. I'm just writing out that whole step there. Whenever you see I squared, you replace it with minus 1. So what's the final answer? Negative 26 plus 13i. And your first reaction is like the reaction when I told you to add 7/2 and 2/3, and you came up with 25/6. You first say, really? Where did you make the 25 from? Maybe I see where you made the 6 from. But let's check this. Inside the calculator, these numbers look unrelated, but they came from foiling this out. So ask your calculator what 3 plus 2i times minus 4 plus 7i is. 3 plus 2i. Sorry, wrong button. 2i times minus 4 plus 7i. Calculator didn't even blink. It just said negative 26 plus 13i. The calculator foiled it out immediately and gathered together the like terms and wrote the answer properly. Now, by the way, there is a proper way to write these numbers. Whenever you write a complex number, people insist that you write the part without the I and then the part with the I. Never write it backwards. Or people will just think you're like uneducated, rude, whatever. When you write complex numbers, you always write the part without the I separate than the part with the I, and you write them in that order. That's called standard form. And it's just a way of everybody writing the same. Don't write 7 plus 2i divided by 5. That's not standard. Write 7 over 5 plus 2 over 5 times I. In fact, that's one of the few times I would tell you not to combine common denominators. This is standard form. This is not standard form. Or if you said 3i minus 7, I understand what the number is. but it's not in standard form. You write minus 7 plus 3i. Okay, where are you? Well, now you can add, subtract, and multiply them. And the multiplying is, you have to admit, something you've been doing for a while, foiling. So now you're really holding out a slim hope that you're not going to have to do this. Because all I had to do is show you the dividing, and you're done. And you kind of logically have to accept it, even though you would ordinarily accept it. So the dividing is something that is harder to swallow. It takes an extra step beyond foiling. So how are we going to divide? And it has to do with something we learned on Tuesday, the rationalizing of denominators. The difference of two squares formula. Think about this. What happens if you take 5 plus 3i times 5 minus 3i? Well, according to your difference of two squares formula, remember a plus b times a minus b is always a squared minus b squared. No middle term, because you have a plus ab and a minus ab. The middle terms add up to 0. Try that here. Pretend you didn't know any better and you're going to FOIL it out. 5 times 5 is 25. Then 5 times minus 3i is minus 15i. And 3i times 5 is plus 15i. See, there it goes. Outside and inside part gone. And then minus 3 times 3 minus 9i squared. So what's 5 plus 3i times 5 minus 3i? Well, this middle part's gone. And remember, every time you see an I squared, you write minus 1. So this is negative 9 times negative 1. This is plus 9. What's 25 plus 9? 34. So when you multiply two complex numbers, you don't always seem to get a complex number back. Now, there's nothing wrong with this number. It's still correct, and it's still a complex number. In fact, you could call it 34 plus no i's. And that's perfectly legitimate. I'll try it out in the calculator. Five plus 3i times 5 minus 3i is 34. Now this is a handy trick that and it's even got a name for it. When you multiply the same complex number twice, but you change the sign in the middle, this is called the conjugate. The conjugate of this other number, 5 plus 3i. This number, change the sign of the imaginary part. This number is the conjugate of 5 minus 3i. These two numbers are called conjugates of each other. And go back and look at original Latin root of that word, conjugate, and this means they belong together. They're linked. They're intimately linked. But the cool thing is that whenever someone tells you to multiply conjugates, then do you see that you don't have to FOIL? How did I get that 34? Squared the 5, squared the 3, 25 plus 9 is 34. Try it again. What's 7 minus 2i times 7 plus 2i? All you have to do is square the 7 and square the 2. Because squaring the I will get rid of that minus 1. And the different signs got rid of the middle parts. So 49 plus 4 is 53. I don't even have to calculate that. Well, I calculated 49 plus 4. Try it out. 7 minus 2i. 7 plus 2i. So this is what I want to say to you. Conjugates are easy to multiply. And this is going to be the trick that I use to divide two complex numbers. You should practice this as many times as you need to before you really believe it. Take these two conjugates. Negative 11 minus 5i, negative 11 plus 5i. All I have to do is say 121 plus 25. 146. And all of a sudden, you're just as fast at this as the calculator. Negative 11 minus 5i, negative 11 plus 5i. In fact, you're faster. You did that in less time than it took me to type it. So what does that have to do with the dividing now? Well, let's think about this. What if I had to divide 3 plus 2i and minus 4 plus 7i? What I really need to do is get rid of this I in the bottom. Just like on Tuesday, we had to get rid of square roots in the bottom. And we also use this trick, a minus b times a plus b. Well, let's multiply the bottom by its conjugate. Why? Because I know when I multiply by the conjugate, I'll have no I. Of course, it won't be legal unless I multiply the top by its conjugate. I mean, I multiply the top by the same thing, excuse me. Whatever I do to the bottom, I do to the top. Now, what happens on the bottom? Well, that's the easy part. 16 plus 49 is what? 65? I can do that instantly. Even if it's a complex number, I can do that instantly. 16 plus 49. Now, that's funny. If you'd never seen complex numbers before today, you can now instantly multiply two conjugates. How about on the top? Well, I got a FOIL. Negative 12, negative 21i, minus 8i. And now be careful with signs when you do this, particularly when you FOIL. You're always careful with signs. But I have plus 2i minus 7i. That give me a negative 14 times I squared. And remember, I squared is always minus 1. So what do I have on the top? Negative 12 minus 21i minus 8i is minus 29i. But here's the negative 14 times the negative 1. That's plus 14. over 65. Now, I'm not done yet. I have to combine like terms. Negative 12 plus 14 is 2. Minus 29i over 65. I'm still not done yet because I cannot write it as this jumbled mess. The rules of complex numbers say you have to write it as separate and the real part first. Here's the final answer. 2 over 65 minus 29 over 65 I. I'm going to check this in our calculator because the first time someone sees this, you say, that's ridiculous. Where did you get that? You're just making that up. But after you practice this today, you're going to start to accept it the same way you accept, 170 divided by 2 is 85. Okay, let's try it right here. Let's get my paper. Well, get this, like this calculator better because there's less glare on the screen. But that's clear. 3 plus 2i divided by negative 4 plus 7i. And I get this crazy decimals. And you say, aha, I got him. Where's your answer? 2/65 minus 29/65. Well, remember, the calculator naturally thinks in decimals, right? You can ask the calculator, can you convert that to a fraction for me? And the calculator says 2/65 minus 29/65 I. And then it's scary. Then you say, oh no, everybody's lined up against me. Even the calculator does this. What am I supposed to do? Well, this is section 7.7. What you're supposed to do is practice it until you can do it. And that's all the problems do in here. Now, if you check out the problems in section 7.7, all they have you do is add, subtract, multiply, and divide these. And after you've learned how to add, subtract, multiply, and divide them, then you got a new set of numbers on your belt. Now, I won't have to put off everything until, some fancy future math class. I can show you what some things you can do with these that might be more practical to you right now. But that's going to have to wait for next week. But first, I just wanted you to believe that there were such numbers and to believe that they were numbers. And the quickest way to make people believe that something is a number, if you think about it, is just like we did. If I show you how to add, subtract, multiply, and divide them, then you say, okay, they're numbers. The dividing takes a little practice and getting used to. So you go ahead and divide some and practice that. But I want you to know you always got your calculator to back you up. So you don't have to do it wrong. You just have to practice until you do it right. Okay? Now I'm going to get these scanned and uploaded. I'm going to get the video scanned and uploaded here. And then you guys can just go have fun with this. You're doing some radical equations for your written homework. I didn't put the complex numbers in there yet because we're going to use them next week still. So next week, I'll show you some things you can do with the complex numbers in a more practical way.
Hey, Professor, can I ask a quick
Go
question
ahead.
before we leave?
Go ahead.
So you were talking about for radical equations how there were, if there's radicals on both sides, then square both, and then you have to FOIL. What if there's two radicals on one side? Would you still need a foil, or would those both just cancel each other out?
No, no. You could leave them both on that side and foil, or it might be more comfortable if you first moved one to the other side and then foiled. You're not going to get out of the foiling. No, unfortunately not. So, yeah, you're going to have to. I think you're talking about one of the written homework problems. I gave you two radicals on the same side.
Yeah.
Yeah. So you got two choices. You could foil it as it is, and the middle term would still have a radical. Or sometimes I recommend, why don't you just move one of the radicals to the other side so you can square once and kill the radical on one side, but then you'll have to still be foiling on that other side.
Okay, so it wouldn't be as simple as squaring both sides and then both radicals would cancel.
Not immediately, no. No, that's a
Okay.
problem. Whenever you have two radicals, you're most likely going to have to do it twice.
Okay. Thank you.
No problem. Okay, you guys go have fun with this. Uh, Complex numbers show up in other interesting places called fractals and fractal geometry. And I'm not sure I'm going to spend too much time there. He just put it in there to entertain you. In this sense, uh, what is a fractal? What is fractal geometry? You and I are really clear on, oh, one dimension, two dimension, three dimension. But do you understand that there are other dimensions, even fractional dimensions? So it is actually possible to have dimension 1.5 or dimension 2 1/3. This is not something you and I talk about every day. So these kind of funny, cute pictures right here called fractals. If you like, you can see them on my website under mathematics, fractals, and I make some pictures for you like this. Now, that doesn't tell you immediately what this is, I understand, but it has something to do with the in-between dimensions. Maybe we could talk about it later, but I got to let you guys go now. Okay, so you have a good weekend and just enjoy doing some of these problems, and I'll talk to you again on Tuesday.